the fact that E equals 4 pi kq can be reasoned out by just considering a sphere of radius r with a charge q at the center. We know that the electric field has magnitude kq over r squared at every point of the surface. And that field is perpendicular to the surface. In other words, that E dot n would just be equal to E at every point of the surface. So that the area, since the area is 4 pi r squared, our flux is just the electric field multiplied by the area. That would be the integral of E dot n dA, but it comes down to electric field times area by symmetry arguments, by the fact that the field is uniform and perpendicular to the surface at every point. We multiply that and we get 4 pi kq. So it's certainly true in the case of a sphere. Well, Gauss's law tells us that it's the case for any shape. If you have any closed surface, the flux, the integral of E dot n dA over the surface of that, over that surface is equal to 4 pi k times the enclosed charge. Now, for most surfaces, this is not going to give us a whole lot of good information about the electric field, but as we saw for the cylindrical surface, where the field is uniform and where we can easily calculate the area, and where the field is always perpendicular to the surface, we were able to derive an expression for the field of a long line charge at a point close to the line, much closer to the line than to the ends. If it was an infinite line, then that would work for any point, because any point is much closer to the line than it is to the ends, which are out there at infinity. Okay, well, let's apply this idea now to the case of a plane distribution of charge. We could imagine this blackboard to be covered with a uniform charge distribution. Charge density, call that charge per unit area, now is going to be sigma. If we take a point close to but not exactly on the surface, we're much closer to the surface than we are to the edges. So from the point of view of any such point, this really constitutes an infinite charge distribution. Now, that's a little bit of a hand-waving argument, a little bit vague, but it can be made very rigorous. Okay, well, let's take just some portion of the area of such a surface. Now, I've drawn this in 3 dimensions. Here's an x, y, z coordinate axis to kind of orient you to the 3 dimensions. And we take some small area of a very large distribution. And I put some plus signs here to indicate a positive charge. The same argument would work for negative charge. Your sigma would just be negative. So any formula we get, or any result that we get here, any symbolic result is going to work whether this is positive or negative. What we do is we construct a box. Now, a side view of that box, here's the charge distribution from the side, just looks like a line, and we have charge emanating out from in both directions on both sides of this distribution. So we imagine turning the blackboard this way, where you're looking at it end on, and what we do is we construct a box through the surface. Now, that box here is going to match the area, if this is the front and this is the back of the box, the area of the front and the back is going to match this area, and these sides are going to be perpendicular to the plane of the distribution, and I should maybe indicate that these are perpendiculars. Okay, so you can kind of visualize the box. We've got a box on both sides of this. If we were to draw a box for this thing, for a small region, let's say for this region right here, then the box would come at the camera out of the board, and it would go on the other side of the board similarly. Now, symmetry arguments can again be used to show that the field is always perpendicular to the distribution at any point that's not too close to the edges. That's always a qualifier. So that the electric field penetrates the box only along the front and along the back. Along the sides, which are perpendicular to the plane of the distribution, the field doesn't penetrate at all. The normal is out this way from this part of the end of the box, and the field is this way perpendicular to it. Dot product is 0. So there's no field penetrating the sides or the bottom or the top of this box, only the front and the back, and we can visualize that based on this picture. So the question then is, what's the area of the box that's penetrated by the field? Well, we had a question about that. Does the field penetrate it just on one side or on both sides? And the answer is it penetrates on both sides. So that's the area of the front plus the area of the back. That's 2 times A, if we consider this region to have area A. It follows then that the field is what? Well, how much charge is enclosed by this box? Well, total charge enclosed is sigma A, the charge per unit area multiplied by the area. So total flux has to be 4 pi k sigma A. The electric field then is the total flux divided by the area, and that comes out very easily to 2 pi k sigma. So again, we've been able to use Gauss's law and a symmetry argument to construct a box and derive the field of a plane distribution of charge at points close to the plane, much closer to the plane than to the edges. The striking thing about this is that the field doesn't depend on how far you are from the plane. As long as you're not far enough, as you would be if you were this far out, where the distance from the point to the plane is not much greater than the distance from the point to the edge. At this point, it's certainly closer, but it's not closer by a large factor. It's only maybe twice as close. So it would not apply to a point out here. This formula would not apply to a point out here on this plane. Now, if the plane was much bigger, let's say the whole wall of the room, then at this point we'd still be pretty safe. We're still much closer to the plane than to the edges. As long as we're much closer to the plane than the edges, this holds, and the field doesn't drop off until we get out to the distance where we are closer to the edges, where we are at a significant, at a point where the distance from the plane is not too much greater than the distance to the edge. This then no longer holds, and the field will start dropping off. And if you go further and further away, this board would shrink comparably to a point. So you would basically have the field of a point charge at that distance.